Now let's see how the laws of logic work for quantified statements. Okay, so let's look at a sort of summary here. So we have certain laws for the universal and existential quantifier. So this first one is that if I have for all x, p of x is true, then p is going to be true for every c. C is one of the x's, so it's going to be true for every element in the universe. Okay, so C is like a specific element, but for all x, p of x is true means p is going to be true for every single element. So that's called universal instantiation. Now universal generalization is backwards. So if p of c is true for any arbitrary c in the universe, so that arbitrary is very important, then you can say that for all x in the universe, p of x is true. So that's the universal generalization. Okay, so c here is not a specific c, it's an arbitrary c. All right, next one is that if there exists an x such that p of x is true, then p of c is true for some element c in the universe. So that's existential instantiation. And backwards from that, so if p of c is true for some element c in the universe, then you can say that there exists an x in the universe such that p of x is true. So existential generalization. So for this one, this element c, it just can be one specific one. It doesn't have to be an arbitrary one like the one for the universal generalization. And we have like two basic laws. So law of detachment that we've used before. This is for every x, if p of x, then q of x is true, and p of a is true, then q of a is going to be true. All right? And the indirect reasoning says that for all of x in the universe, if p of x, then q of x is true, and not q of a, then not p of a. So that's the indirect reasoning version for quantified statements. Okay, so let's look at an example. So we're gonna have these premises here. All right. Let's pick blue. Everyone in this discrete math class has taken a course in computer science, and Maria is a student in this class. They imply the conclusion Maria has taken a course in computer science. So let's translate this. All right, so everyone in this discrete math class has taken a course in computer science. So that says for all people, if the person is in discrete math, then they have taken a class in computer science. Right, so that's the translation of the first premise. Right. And then it says, and Maria is a student in this class. Okay, so we can say CM is true. Okay, so Maria is a student in this class. Oh no, that's not it, because people in this class are D's. All right, so and DM. All right, so Maria is a student in this discrete math class. Okay, so these are my premises. And I want to imply the conclusion that Maria has taken a course in computer science. So I want to show that CM is true. All right, so this is how this is going to work. So we'll start with the premise. This premise here. Okay, so for all x, if dx, then cx. So if the person is in a discrete math class, then they have taken computer science. So that's a premise. Okay, and then we're going to say that this implies dm. If dm, then cm. Okay, so this second statement comes directly from this first statement, by the universal instantiation. Okay, so you can see how that works. So this is like a compound statement, but it still works. So if that statement is true for all values of x, for all people, then it's going to be true for Maria, for this particular person. All right. Okay, then we have, dm is true. Okay, and this basically gets translated to, this is not a predicate anymore, it's just a regular preposition. So if dm, then cm, but I know dm, then this is going to imply, if I combine these two together, 2 and 3 are going to imply that cm with the law of detachment. All right, so I kind of took it step by step. If you look at the law of detachment the way it's written here, right, this exactly looks like that one. So you can sort of, from this line, this is just the law of detachment, but I sort of broke it up to see how the universal instantiation works here. Now let's look at this problem now. Okay, so show that the premise is a student in this class has not read the book, and everyone in this class has passed the first exam. Imply the conclusion that someone who has passed the first exam has not read the book. So first, let's translate. So kind of we have our variable be the person. So to translate the first premise, a student in this class has not read the book, we're going to say there exists a person who is a student in this class and has not read the book. All right, so Cx is that this X is in this class, and B is that X has read the book. All right, so that's my first premise. Okay, everyone in this class has passed the first exam. So for every person X, if they are in the class, then they pass the first exam. All right, so Px is X has passed the first exam. Right? So these are my premises. So this and that needs to imply the conclusion. Someone who has passed the first exam has not read the book. So there exists a person who has passed the first exam and has not read the book. Oops. All right, so we're going to use the laws of logic to show that this is a valid conclusion from these premises. All right, so let's start it. So we're going to start with there exists a person in this class who has not read the book. This is a premise. Okay, so now we're going to say CA, if CA then not BA. Nope. Sorry. I wrote this wrong. Okay, so the first premise is an AND here, right? There exists CA and not B, CX and not BX. So we're going to say CA and not BA. So this is existential instantiation. Okay, which means that if there exists a person in the class who has not read the book, then A is that person. Okay, Okay, so this is basically we're giving a value for x. So this is a premise that doesn't depend on a variable. Okay, so with the laws of logic, I can say CA. This is this conjunctive simplification. There, conjunctive simplification. All right, now we're going to look at for all x, if a person is in the class, then they pass the first exam. So that's the premise. All right, and we're going to use the universal instantiation here to say if this A person is in this class, then they pass the first exam. So this is universal instantiation. Okay, now we can see that I can put together 3 and 5. If we put together 3 and 5, CA, therefore PA, and CA, this is the law of detachment, therefore PA. Okay? Yeah. Now, going back to number 2, I'm going to, this is an AND, it's a conjunction, and I'm going to separate the not BA, and this is again by conjunctive simplification. Okay, and then I'm going to put together these two. I'm going to put together 6 and 7. Okay, so this is number 8. So 6 and 7, PA and not BA. This is conjunctive simplification going the other way, taking two separate statements, making with and in the middle. Okay, and the final step, there exists an x such that P of x and not P of x. Okay, so this is existential generalization. So going from an instance of the statement to the general one. Okay, so this is existential generalization. All right, so that's our conclusion, that's our proof. Okay. Okay, let's do one more. So we want to show that, prove that this statement, these premises lead to that conclusion. So we have for all positive integers n, if n is greater than 4, then n squared is greater than 2. Is true. So that's a premise. Show that 100 squared is less than 2 to the 100. Okay, so let's see, we have some statements here. So let's make this be P of n, and then this is Q of n. So my premise says for all positive integers n, if Pn is true, if n is greater than 4, then Q of n is going to be true. Okay? And we want to show this statement. We want to show that 100 squared is less than 200 squared. Okay? So let's actually do this. All right, so we're going to say and P at 100. Okay, so this is also part of the premises. So basically, this right here is P at 100, and I want to show that Q at 100 is true. Okay, so that's how you set this up. So the premises say that if for all positive integers, if n is greater than 4, then n squared is going to be less than 2n. All right, so show that 100 squared is less than 200, then I'm going to say if p at 100, so if I have 100 squared, then q at 100 is going to be true. Okay, so we can see that basically this is the law of detachment. Right, because it's the setup for the law of detachment. So if for a general n, if you have if p at n, then q at n, and you know that a p is true for a particular value of n, then the q at that particular value of it is true. Okay, so again, here Pn is the statement that n is greater than 4, and P 100 is true because 100 is greater than 4. Right. And Qn is the statement that n squared is less than 2n. Q 100 is going to be that 100 is less than 2 to 100. Right, so that's it for the section on quantifiers. So pre-watch this lecture and then take notes, kind of write down questions that you have along the way, and come to the live sessions, and I can clarify any questions that you have.